Hello everyone, today let's solve the problem number 50, power this one, power of x comma n. Right, so here we have been asked to implement the power of x comma n, which calculates x raised to the power n basically, right? So when I hover over here or when I click on this one, so just give me a second here until it loads. Actually see here power, so this one says that we have to compute the power of this one val array elements, right? So it returns the val array containing the results of the power operation on all the elements on the same order. The result, this one, the results calculated are x raised to the power y, right? So here the function calls power unqualified once for each element on both x and y. If either a single value, this one t value, it is used for all the calls, right? So this is what they have given. They have given us examples as well. You can just look into it. It's easier to understand. It's very easier. It's very easier to understand basically, right? So let's move on with the example 1 here. It's the first example we have here as x equals 2 and n equals to 10, right? So this will be 2 to the power of 10 basically, which leads to the output this one 1024. And this one you have to observe one thing here. We have 5 decimal places here, right? So this one also we have to keep in mind, right? So 1024, after that we have 5 decimal places followed by this one 5 zeros. So here we have been given 2.1, for the input also the same 2.1 followed by 4 zeros and n equals 3, right? So 2.1 to the power of this one 3, the output that we need to get here is 2 followed by 5 decimal places. Here in this case it would be 26100. Same goes with example 3 as well, right? So this is fine, I believe. And we can have the negative value as we'll see here, and we have -2 here also. That also we have to keep in mind, right? So this is fine, I believe, right? So this is the question, right? So we are done with the question part. So let's do one thing. Let's quickly discuss the approach and approach followed by the complexities, and then let's write the code. To solve this particular problem, we'll be making use of the simple math, or we'll be going with a simple math here, right? So we will be making use of, let's consider this example itself, right, for the approach, so that it will be easier for us to understand. So we will be making use of the exponentiation by squaring, right? So this is nothing but the mathematical property, right? So repeatedly squaring the base and then using the binary bits of the exponent, that's what we'll be making use of. So here in this case we have n equals 10. So the first example that we have considered, right? So we have n equals 10 here. So let's do one thing. Let me consider this one itself. N equals 10. We have n equals 10. 10 in the binary, this is represented as 1010, right? N equals 10 in the binary, it is represented as 1010. And now we need the factors for the bits 8 and 2. We need factors for the bits 8 and 2, right? So first we'll be going with the result variable. I'll just go with the res here, or let me go with the r. This is fine, right? This is nothing but the result variable. Consider this one is resulting variable. So this one I'll be initializing this one with the 1, and also base we are considering the base, right? So b initially we'll be going with the 2, and exponent e, so e, this one n we have been given 10. So e, nothing but the exponent, will be considering this one as 10. Will be considering this one as 10. B, nothing but the base b, this one we have been given 2 here, x equals 2, right? So this is fine. This is nothing but the result variable. Initially we'll consider this one as 1, right? So e is nothing but e is even. So we will be going with a, or we will square the base here. So when we square this one 2, so this will be basically 4, right? So this will be 4. Next step, b will be 4 and e will be 5 basically. E will be 5. So this is fine. I believe this is fine. Now e is odd, right? So previous step e was even, now e is odd. Quite obviously we will be going with the result equals result into b, right? So we'll be going with the result equals result into b. Nothing but result will be here in this case result equals result into b, in the sense b is 4. So 1 into 4 will lead to 4 itself, right? So result becomes 4 here basically. Result becomes 4, and we have to square the base. Nothing but base b becomes 16 here, right? Also one more thing, this one e becomes 2 now, e becomes 2. So result becomes 4, base becomes 16, and exponent e becomes 2 here. This is fine. Now e again it will be even, so we have to square the base. Now we have the base 16 here. When we square the base becomes 256. 16 square is nothing but 256, right? So we know this, right? So exponent becomes from e exponent from 2 from the previous step. Now the exponent becomes 1, right? So this is fine. Now the last step is e will be odd, right? So we will be going with this formula. This time we'll be going with the result equals this one. What do we call? Result into b, right? So result equals result, we have 4 here. Result into b in the sense 4 into 256 basically, right? So result we have 4, and b we have this one 256. So this one will be result equals 4 into 256, right? So result becomes 4 into 256, nothing but here this will be 1024, right? So this will be 1024, and exponent becomes 0 finally, right? From 1 exponent becomes 0, right? So now we will stop as exponent became 0 here. Now in this step we are gonna stop, right? So we are gonna will not proceed further, so we'll stop here. So the result that we got here is 1024 basically, right? So this yields 1024.0 n logarithmic n multiplication. So now we got the output 1024.0, right? So this one in the code we'll be writing that one meaning. So here we have to go with the 5 decimal places, that we'll see in the code itself directly, right? So the output that we got here is 1024 basically, which is equivalent to the output that they have mentioned for the example 1 within the question, right? So our approach works absolutely correct. As we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part, right? So what will be the time complexity here? The time complexity would lead to big O of logarithmic n, right? So this one will be big O of log n, right? So this will be the time complexity, overall time complexity. So what will be the space complexity here? Space complexity would be big O of 1, right? So space complexity would be big O of 1. So the time complexity would be big O of log n, and the space complexity of would be big O of 1 for the code that we'll be writing in the future, right? So this is fine. So now we have the the time complexity and the space complexity along with the approach as well. We have discussed the complexities and the approach. Now as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the code actually, right? So first thing is so let's convert the exponent to the long, right? Just for the safer side. So this I'll do one thing. I'll just go with the long e equals n basically. Next step would be, if the exponent is negative, then we have to invert the base and make the exponent positive accordingly with the approach that we discussed. So this one, if exponent is greater than is less than 0, sorry, not greater, negative, right? If it is less than 0, then x equals 1.0, then we have to make it positive. So 1/0, 1.0 by x. So this is fine. Exponent equals, I'll just assign this one to the minus this one. So this one, x equals 1.0 by x, is nothing but the mathematical rule x to the power of minus n. In the sense we are going with a 1 by x to the whole to the power of n basically, right? So this one, e equals minus e, whatever I have given, this one we are just negating the exponent safely because e is very long, right? So I hope this part is completely clear, man. Next, let's do one thing. I'll just come out of this one entirely. Now let me initialize double result equals 1.0. So this is nothing but we are just going with a result accumulator that start at the multiplicative identity, right? So next let's go with a while loop. So we have to loop until all the bits of the exponent are processed. So this one I'll just go with while e greater than 0. So this one would be let's go with the simple if condition. Nothing but if the current least significant bit of E is 1, then we have to include the current base into the result, right? So this one I'll just make use of if E logical AND operator 1, if it is equivalent to the value 1, then we have to include the current base into the result, right? So this one I showed this one step by step. Result equals result into x, right? So this one will be result equals result into x. This is fine, man. Now let's do one thing. We are left with only quite a few things. Now we have to square the base for the next bit, right? So this is nothing but the mathematical repeated squaring. Also we have to shift the exponent right by one bit. So this one I'll just go with x equals x into x. So this is fine. Also we have to shift the exponent right by one bit, right? So this is nothing but e right shift operator. We are left with only one part, so we have to finally return the this one computed x to the power of n. This is nothing but the final computed x to the power of n. So that will be stored in the resulting variable res. Res is what we have considered here. Somewhere I have considered, right, this one double. Initially I have initialized this one to 1.0. Now let's return the resulting variable. This is fine, man, right? So let me let me hit the run button. So we have I have missed the semicolon here, so let me hit the run button again. I hope this works. You can clearly see here the sample test cases are getting passed, so let me hit the submit button quickly. So now we are done with the this one, what do we call, coding part. So here we are so all the test cases are getting passed, means whatever the code that we have written works absolutely correct for all the test cases. I hope solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.